right, and we are on to our next section, which is auditory processing notes. And we're going to be talking about how we process sound in our environment. And like we said with what I said in about the visual processing, and we see like energy, like wave, we do the same thing with sound waves. It's all in our environment, and they are all like everything right now that I'm saying right now is being it's creating these waves, and then it's going in through the speaker, and it's going through your computer, and then you're able to, your ears pick up these sound waves that I'm letting out, and then it sends it to the brain, and then your brain tells you what word I'm saying. So pretty freaking cool when you think of it like that. Like, wow, we're able to see and how fast our brain works to be able to do that. All right, so we're gonna start with sound waves, and our amplitude, which is the height of the wave, is going to determine the loudness of the sounds, okay? And then the frequency is basically the length, okay? And that's gonna determine pitch. Now, you definitely need to know the wavelengths and what it means so as for sound. So when it has a short wavelength, there's high frequency, okay? So high pitched sound. And just for this one, you're gonna draw the sound waves again, but now only focusing on the sound wave one. So a long wavelength is going to be low pitch sound, great amplitude, loud sounds, and small amplitude is soft sounds, okay? And then the way that it measures sound waves is going to be by decibels, okay? That's how we measure it. And just to give you an idea, right? So normal conversations about 60, okay? Once we get here to this point is where we start having anything above 80 is going to start, or 85 decibels is going to start creating hearing loss, okay? So, and just so you guys know, right, when we're putting those AirPods in our ears, or even those, like any type of things directly into our ear, we're actually using at the loudest is about 100 and something. And it kind of depends. So it'll fluctuate. It's like from 90 to about 100, 120, on the loudest level. So we'll definitely talk about that. But if you want a job in the future, definitely go into ear, nose, and throat doctors, because we're all going to be losing our hearing. So you'll definitely have a job during that time, okay? So we'll talk a little bit more in class about that. But I always tell my students, I'm like, you want a guaranteed job, go into ENT and you'll have a job for sure. All right. So this is kind of like the same thing with with the eyes. You also need to kind of draw a little idea of what the ear should look like. If you want to draw it out, take a picture, whatever, add it in there, or just write out the pieces, you can. I will be giving you a diagram of both of them so that you could put the function, okay? So I'm going to talk about a couple things on here that you need to know. So this is basically the outer ear, okay? And now the outer ear is basically where it's going to channel these waves into our auditory canal, right? They come into here, and then it's going to, those wave lengths or the sound waves are going to hit the middle ear. And the middle ear is basically where we would call the eardrum, all right? And then the eardrum, you have three tiny bones, and they are called they're here. I believe they're here somewhere. I guess they're not. Oh yeah, they're right here. It's called the hammer, the anvil, and the stirrup. Okay, those three bones are what basically is going to receive the sound waves, and those bones are going to then send those sound waves into what is the inner ear, which is your cochlea, okay, which is this kind of snail-like thing, or it's called the semicircular canals are here, and then but this is your cochlea with semicircular canals. Now in the cochlea, which is the very very important part of your ear, it is going to be the one that has transduction happening inside there. Okay, so transduction happens inside the cochlea, and you'll see this is what the cochlea looks like inside here. And they're basically little hair cells inside there. And the vibrations, okay, make that cochlea membrane vibrate, and then it'll convert it to neural energy. And then there, it's going to send it to the auditory nerve. Once it does transduction, sends it to the auditory nerve, and then the auditory nerve sends it to the brain, and then the brain perceives what you just heard. Okay, so make sure to pause this video so you've written down all of the functions of those things. Okay, now once we have that, so that's basically what the hearing, how it works. All right, now let me go on to hearing loss. Definitely need to know about hearing loss. So hearing loss, we have what's called sensory neural hearing loss. And this is where we're going to damage our nerve cells in the cochlea. So those little hair cells, after when we are listening to high levels of decibel, or just even over time, we're going to lose those hair cells, okay? Because they're like cells, like everything else. They start deteriorating as we get older. Now, the problem is that if we're exposed to prolonged loud noises, we hear those hair cells get damaged a lot faster, okay? Now, the only way to repair the cochlea, the hair cells, is through what's called a cochlear implant, okay? And some people are actually born with damage to their cochlea. And so they may even just get a cochlear implant, okay? And the cochlear implant is basically it's a severe surgery, and if you see here, they will it's connecting to the temporal lobe, and this is the part of the implant that is going to do the transduction, okay? So it's going to pick up on the sound waves, it's going to convert it into neural energy, and then it sends it to the brain. But it's not as fluent as like how we speak, like how we would hear a regular talk. It's kind of like robotic, okay? Because again, it's a foreign object, and it's not going, it's pretty slow. So some people don't like it. It's very controversial with the deaf community. Some people are like, it's great because you get to hear, like people get to hear and they don't have to have, hearing loss. But others are like, well, if we do this, then we're removing like people from the deaf community, which to them, they communicate, through sign language, they still have a language. So there's a little information on that. Then you have conduction hearing loss. And conduction hearing loss is basically where there's damage to the structure to the middle ear, to the middle ear or the inner ear, so the bones or the actual structure of the cochlea, okay, or any of those tubes. Now, this can only be fixed by hearing aids. Okay, so a hearing aid just basically amplifies, the sound waves, and then it sends it to the cochlea to then send it to the neural connection, or the neural impulse to the brain, and then it processes it, okay? But a hearing aid, they can't like turn it off, which if you ever seen somebody that's older, sometimes they're like, oh, I just don't want to hear anything. And then they'll just turn off the hearing aid, and then they don't get to pick up those sound waves. Okay. And then there are theories on how we hear. Okay, and the two theories are, the first one is place theory. And place theory is basically we're going to hear different pitches because, so this is based on like pitch, because there's different sound waves that trigger different places along the cochlea's basilar membrane, all right? So the basilar membrane is, and again, hold on, my iPad is like activating Siri. Okay, the basilar membrane, which is inside the cochlea, and you definitely need to know about the basilar membrane. This is where the cells are, and does transduction happens there. So they say that in the cochlea, there are different areas that pick up pitch. Okay, so these are like the different hertz that each section. So depending on where the wavelength hits, then that is going to be the pitch that we hear. Okay, so that's place theory. The problem with this is that it does not explain, and make sure to write this down, it doesn't explain how we hear like really low pitch sounds. Okay, like that doesn't reach like some of these hertz. And it's very difficult to localize where it's happening in the cochlea, okay? But it explains how we hear high pitch sounds, okay? So that's a good thing about place theory. Then we have frequency theory, and frequency theory is basically where the brain is going to identify the pitch by monitoring the frequency of the neural impulse that is traveling through the auditory nerve, okay? So the way that this works is that the basilar membrane is going to vibrate due to the sound wave, and then it's going to trigger a neural impulse to the brain. Those sound waves have about a frequency of about 100 waves per sound. Then, like, so if a sound wave has a frequency of 100 waves per second, then 100 pulses per second travel up the auditory nerve to then determine the frequency of the sound wave, okay? The problem with this is that neurons sometimes cannot fire faster than, let's say, 1,000 waves per second, but we can still hear these high pitch sounds, okay? So wait, sorry, like low pitches. So this is one that, like, the place theory explains high pitch sounds that we hear. Frequency theory explains low pitch sounds, okay? And then these combinations allow us to hear our range of different pitches, okay? And that is basically it for hearing. That was easy.